Hilder Math 126 fans, I'm going to do a series of videos on how we set up double integrals. I think it's really fascinating, the volumes we can compute. And for years, I've been saying that almost all of the chapter 15 problems are the same, meaning you have an integrand, you draw the region, you give the bounds, you evaluate. So it doesn't matter. So part of what confuses people is the questions have lots of equations. So you kind of need a plan of attack. But we're going to talk about the beginnings of a few of the homework questions, and I'll show you some visuals, hopefully to get you excited about this. And I will do a separate one for each section. The truth is, it's the exact same approach for all of chapter 15. 15.2, 15.3, everything we do is this same approach. The subtleties of how we give bounds, and then the confusion sometimes students have about labeling regions are the challenges, but a lot of that doesn't have anything to do with 3D. It has to do with your 125 skills. Okay, so I'll do one for each section. I usually just do one part, but since I'm making these videos, I'll break it into 3 parts, and I'll just basically repeat for 15.2 and 15.3. But that might be helpful that way. Okay, so here's a problem from the homework. It says find the volume of the solid under this plane and above this rectangle. Apologies, my cat is meowing in the background. Okay, so step 1. Is there anything here that describes height? Well, the only thing here is this. So we're going to solve for our z's. That's our integrand. So I can say that 4x plus 6y plus 17 is equal to 2z, which implies that z equals, let's see, let's divide everything by 2. 2x plus 3y plus 17 over 2. That was relatively painless. That describes a height. Now, if you go on to take Math 224, we talk about how to choose whether you'd like to set it up as z as your output or y as your output or x as your output. And you still could do that here. But in 126, every single problem you can do as z as your output. We set up the problems that way because there's other things to think about. Okay, that's step 1. So there's your first example of step 1. That's the surface. It's actually a plane. So we're under that surface. Then the second thing, and independent, is the region you're drawing on the ground. Now in this case, the region we're drawing on the ground is just a rectangle. So it's kind of the easiest of the situations. But again, this is in 15.1. It says x needs to be between -1 and 2, and y needs to be between -1 and 1. And we'll talk about how as you get to a general region, you have to think a little harder about how you want to choose to set things up. But in this case, it really doesn't matter. Step 3, give the bounds. And that's where you're going to have choices over the next few lectures. You're going to decide how you want to describe this region. At this point, you have your choices just whether you want to do it in terms of x first or in terms of y first. So you could say y goes from -1 to 1, and then the integral from -1 to 2 of 2x plus 3y plus 17 halves. And it looks like I have the x on the inside and the y on the outside. Compute. Step 4, compute. So that's how I think about everything in chapter 15, is those same steps. Now that you can see there's some subtleties I mentioned here, and we'll talk about some of these in the problems. So then you will compute. But before I go on, I want to show you that that is interesting. Visually, this is this object. So we have this region on the ground, which is this little, let me adjust my view slightly, apologies. It's that region on the ground. Let's see, x is here. Y goes from -1, x goes from -1 to 2, and then it's up to this surface, that plane. So it's kind of an interesting little volume that we can find. This is your general technique for a volume. That's not a volume of revolution or something else. It's cool that we can compute that, in my opinion. Okay, let's play the game again. Here's another problem. So it doesn't matter what words are in there, that it says hyperbolic, paraboloid. That's actually trying to help you if you wanted to visualize. Step 1, are there any z's? Step 2, draw the region. So here we go. 1, yes, there's a z right here. 3y squared minus x squared. That's the surface. This is what a double integral does. It follows the volume up to a surface. Step 2, draw your region. The region is x between -1 and 1, and y is between 2 and 1. And that's it. Again, they were trying to help you realize that it's the volume above that and below this Pringles chip thing. But now you can set it up however you want. You set up the bounds. Doesn't matter. I've chosen to do it this way for a rectangle. So I think 1 to 2 was my y. And again, if I have any, the goal here is just ideas. You know, you can let me know. I'm sure I'm making some mistake here, but you're then going to compute. Step 4, compute. Okay, let's see that one. What are we doing? This is this thing. Get rid of this. So the actual surface is a Pringles chip, if I zoomed out, but we're only looking at it above this region. I think it's amazing we can find these volumes with very little effort. So this is a real general approach to volumes. You just have to be able to describe the region on the ground and find the surface. Let's try another one. Here we go. Done. Let's grab this one. Find the volume in the first octant bounded by this cylinder and the plane. Are there any z's? Yep. Step 1, find your z's. So with practice, I don't find these too bad to set up. Even if you're not good at visualizing. Some students go, well, I'm not good at visualizing. I didn't have to visualize to see that was a z. Step 2, I'm going to draw my region. And this will be the first example where something more interesting happens. And I think this will be helpful. So what you typically do is you draw any given xy bounds. Now, first octant means x is greater than or equal to 0, y is greater than or equal to 0, and z is greater than or equal to 0. So the bounds they've given me so far are x equals 0, y equals 0, and y equals 4. Those are the things that all of this implies immediately. And so those are the things I would draw. Y equals 0 is here. Y equals 4 is here. And x equals 0 is here. And at that point, I then scratch my head and say, that is not a region at all. And this happens sometimes. That means either the person who wrote this question messed it up, or something else is going on. And that's what this is about. If you draw the given xy equations and it does not clearly give you a region or a solid, and someone didn't screw up, then that must mean the surface intersects the ground, or the surfaces intersect each other. In this case, the surfaces are this and this, and they're bounded inside here. Do those run into each other? So ultimately, it'd be helpful maybe at this point to try to visualize. There are times when you might have to visualize and realize, oh, I can actually draw this in 2D. It's a parabola and it extends out. But that's actually more than you need to do this problem. You just need to know that the only way this could happen is if the surface intersects the ground. When would the surface intersect the ground? Well, that would be when x squared is 4, when x is plus or minus 2. So the thing we haven't done that's in the first quadrant is x equals 2. Aha! There's our other side. Now we're ready to give the bounds in either order. Maybe I'll just say 0 to 4, 0 to 2, 4 minus x squared, and we have dx dy. So what happened there? Let's see in a visual. So they gave us this surface. Now I'm going to do it in pieces. Let me get rid of some of the sides here. And let me go give the whole surface. So the whole surface is actually this parabolic cylinder. But they said it was in the first quadrant. And you might say, well, why didn't they tell us what the bound was? But you can see that the surfaces hit the ground. So it didn't need to give the other side. So if I go through the sides and see what I get, let's go one by one. This is x equals 2, what I just graphed, that purple. This side over here, the green, is x equals 0. This back side here, sorry, this is y equals 0, and y equals 4 is the purple. The back side is x equals 0, and there is no side. It's just a line. That line is when they meet, which is when x is 2. That's what's going on. The reason we weren't given that as a boundary surface is because it's not a boundary surface. It's just where they meet. Okay, that's the second step. If they give you a bunch of equations and they don't define a region, and they're claiming it's a solid, then the surfaces have to meet. If you just build that into routine, then you'll be able to find it. Okay, that's our first instance of that. Lovely. And it's cool, we're finding all these volumes. All right, last up from this homework, and you still need to compute, I'm just giving this idea. Whoa, look at all those equations. That's when people come to me, is they just see the question, they don't even attempt it, because they go, too many equations. My eyes are going to explode. You find the z's. An interesting thing about this problem is there's actually 2 different z's, and neither one of them is 0. So this is an example where there's multiple integrands. Let's think about what that means. In general, what that means is you're going to have some sort of region on the ground, and you're going to find the volume up to the first surface, whatever that is, and the volume up to the second surface, whatever that is. Let's say this one's smaller. If you find this volume, and you want the volume between them, you subtract. So you don't even have to really think much about these either, which is I want to do the double integral of this. And again, some visualization is helpful. I'm just getting you really far into the problem before you even have to think about it. So unfortunately, I have 2 volumes to compute. Sometimes students go, how can you tell which one is bigger? You don't really have to yet. You just need to recognize that there are 2 different surfaces. There's 2 different things giving heights, and neither one of them is 0. Step 2. Draw the given x and y bounds. Draw the region on the ground. Now in this case, it's x goes from -3 to 3, and y goes from 0 to 2. Oh, it's a rectangle. Nice. So that step was easier this time. Step 3, use your bounds. Here is the moment where you might be able to tell which one is bigger. Grab any point in your region, preferably one like actually inside the region. So how about 0, 1? And you can plug it into both. What happens when you plug in x equals 0 and y equals 1? Maybe I picked a weird point. I think I actually get 1. So that was a bad choice. What about 0, 0 then? If I plug in 0, 0, oh, sorry, I don't get 1. I just can't. This point gives me a z equals 2 plus, and I'm trying to go off the screen, sorry. Hope I didn't do that on a different problem. 2 plus 1 is 3. Is 3 or 1 bigger? 3 is bigger. Over the entire region, this is bigger. So you could, once you realize one is bigger than the other, you can compute them separately, meaning like this is bigger, and this is smaller. And I'll show you some visuals of this in a second. Or if you want, you can put them together. In this case, that's somewhat advantageous because you can do 2 minus 1 is 1. It's a little less computation. Then you can give the bounds however you want to do it. How about -3 to 3 and 0 to 2, 1 plus x squared, y minus 2 squared. Let's see, that's dy dx. Hopefully I've lined these things up correctly. Compute away, and it's the volume. It's the volume between. If you happen to get a negative, then you've done it in the wrong order. And if you wanted, you could just compute them separately and do the smaller number subtracted from the bigger number. Okay, let's see that in action. So here we go. Here's this surface. I'll make it bigger here. And I hope this is valuable. Let me know if this is valuable to you. What we're doing is they gave us this region on the ground. It looks like this. They gave us this surface, which actually is a paraboloid. It goes up like this. It's a paraboloid. And we're finding that volume between them. The other surface is z equals 1. So let's restrict to just that region. I think that's a pretty cool looking volume. If you don't include the 1, it will just find the volume all the way to the ground. If you include the 1, it will find the volume between them. It's that thing right there. Again, I find this pretty interesting that we can compute all these volumes. So we got to experience a few things there. Let me know if this is helpful to you. But I'm trying to make the case that I have tried over many years to hone this. What is your process? And I've made it simple and short, but you need to understand how to use it. And I hope this is helping you.